All right. If you have anything, use your mic to interrupt me because I'm not looking at your message now. Okay, today we will move on to the new topic on power supply. All right. Okay, I'll get started now. I think power supply is not something new to you. You have heard it before. All right. Used in many places, of course, many appliances, many gadgets. All right. Okay, but of course now we go into a bit more detail what actually happens before any appliances or, for example, computer or laptop being powered up. Okay. So before we start, we have to first acknowledge one thing that is important, that voltage that is coming in to our power point are all AC, right? Alternating current voltage. Of course, if we want to, for example, power up our laptop or desktop, we need to have AC voltages. So there is a kind of conversion here. So take note, this one very first thing important. From AC, I need to convert to DC. Example, your laptop is powered by DC. Most of the, if a motherboard, a fan, or whatever inside your laptop or your desktop. Okay, can? So that's the first thing. So incoming AC, convert to DC to serve the needs of your appliances. Okay, there are three important parts of the power supply that all of you need to know. All right. The first one is a rectifier. Number two is a filter. And then there's a regulator. All right. Here they identify them as three different circuits. Of course, everything lumped together is inside your power supply. What you will find in a typical power supply will be these three circuits, so to speak. Okay? Yeah. So, okay, now let's move on. Okay, just as I mentioned already, we of course first thing need to do is to convert voltage from AC into your suitable voltage. All right. A transformer, I think most of you probably have heard before. Okay. Basically, they are used to step up or step down. Here they say step down, but sometimes also you can use it to step down, step up the voltage. Okay. But in general, from the power source, let's say the power general plant, power plant. Let's say in Singapore, in Singapore, there's one. Okay, very high voltages are being sent from the so-called power plant. But of course, right up to our homes and offices, our voltage supply is 230 volt AC. Okay, so along the way, the very high voltages are being stepped down. That's probably what they mean. Okay, but doesn't mean there is a step up. Just to clarify for all of you. Okay, so they step down to voltage as used in Singapore. 230 volt AC, 50 hertz. Okay, that's our power supply in Singapore. Okay, then of course the next thing after you step down to 230, now you plug your appliances to the power point. First thing, there's a rectification. Okay, just as I mentioned, you need to convert, all right, your AC to DC. Okay, that is an important thing you need to do. There's a conversion. Okay, and then the component that is doing it is called a rectifier. Okay, we come to that later and look at how this rectifier works. So now it's just a general introduction to you to the three different circuits, what they do. Okay, so rectification done by rectifier, and that is to change from AC to
Hello.
To DC.
Hello, sir. I'm here.
Okay, the next one we are talking about is filtering. All right. Basically, is to smoothen out the DC circuit, or eventually output to your device. Okay, this is a smoothing circuit. Sometimes we call, because after just before the smoothing filtering, your DC is like a ripple. Those current water ripples like that. So it's not really flat, so to speak, not smoothened. So the filter circuit will do the smoothing of the pulsating. The pulsating means the signal is like something like that. Okay, it's not flat. So after the filter, of course, you expect to see a very nice DC line, a straight line, I mean. Okay, so yeah, this is what the filtering does. And then the third circuit also very important, which is called regulation. Basically, what does it mean? All right, this is to make sure there is a constant output voltage. That's the key word. All right, because you don't want your output voltage to change. Okay, if it's supposed to be, let's say 5 volts, it's supposed to be 5 volts and it should remain at 5 volts. Okay, and not suddenly drop to 3.5 volts or goes up to 6 point something volts or whatever. So the word regulation here is, to make it simple, you want to provide a constant output voltage, which is very important to computing equipment especially. Very, very important. Because some of you may not have come across, but in some cases when voltages change, because the power supply has problem, and it also can cause some of your device like inside your COM, like the hard disk, all right, to be corrupted, yeah, to the extent. Okay, so yes, so this is very important. Okay, that's under regulation, and it's achieved by a regulator. Many a times we will call it a voltage regulator. Okay, Ken, so I already run through the 3 circuits in general. So now this block diagram here will probably help you to see things in better perspective. Correct? Okay, first from left, this is your AC coming into your power point. Your transformer, remember just how what it did is step down the voltage. Then this one done. After you step down, you comes in, you need to convert from AC to DC. That's why you get a DC here. Here is still an AC. Okay, here still AC. Yeah, just better write first. Okay, in case, yeah, you're thinking how come. Okay, alternating current still coming in here. After the rectifier, it becomes DC. Okay, the word pulsating, just how I mentioned, is not very smooth. You have something like that. Okay, or it's not a very flat DC voltage, so we call it a pulsating DC. And that's why we need a filter. All right, your filter here to smoothen the pulsating DC, and probably you have a nice flat DC signal. Yeah, but they use the word probably still unregulated, means not stable. Okay, may change a bit. And finally, of course, the voltage regulator will take care of the unregulated DC to make it a regulated output supply. So finally, you will get a very nice straight line of the DC at the output. Okay, so this diagram is very helpful to you if you read, and then you may not be too sure. So from left to right, that is probably the entire process of a power supply. Okay, the main blocks are the circuits. Okay, so transformer, step down voltage, but still AC. AC go through rectifier. Rectifier convert your AC to DC. DC comes in because it's still pulsating or not very smooth. The filter will smoothen the signal and you get nice straight DC. But it's still unregulated, meaning it's still not very constant or stable. And finally, the voltage regulator is the one to keep a very constant output voltage for you. Example, 5 volt DC, and it always stay at 5 volt DC. Okay, it's not supposed to change, right? That is the meaning of voltage regulator. Okay, any question up to here? Anyone? Any question for me at the moment? Okay, with no question, I continue. If have, please stop me. Thank you. All right, now we go a little bit more depth all right, on each of the circuits, starting with the rectifier, all right. Okay, again, what is a rectifier circuit or rectifier? It converts, just remember the keywords, AC voltages to DC voltage. Okay, that is the purpose of a rectifier. Okay, then of course we move on to introduce to you three types of rectifier. Of the half wave, the full wave, but they call center tap, and then the full wave bridge rectifier. Okay, don't worry, further down we will look at the circuits and then we see how it works. Okay, so for now, take note of these three: half wave, full wave center tap, and full wave bridge rectifier. Okay. The very first one, half wave rectifier. Okay, you follow, I don't think it's difficult to understand for this one. Okay, I hope you still remember this diode, very important component, which all of you seen many times in the lab. Okay, remember the last lesson I told you about the forward bias and the reverse bias of the diode, correct? Okay. Now, can you follow me so that you understand why the waveform started with A, C, and then becoming like that on the right-hand side? Okay? All right, now I start. Okay. Let's say now the AC flows as usual, but imagine now the positive cycle comes in. Okay, I think positive, and by the way, this is the positive side of your diode. Okay, this is the negative, the cathode. Okay, when a positive cycle, half or rather, of the AC signal comes in, so positives and positive, we say forward bias. I hope you remember. When you say forward bias, that means current will flow through. Yeah, will flow through. So your output, you see the positive cycle. Are you okay first? All right, I'm looking at this one, positive cycle only. Comes in, because positive to the positive of the anode of diode, we call forward bias, and then current will flow through. All right, and flow through the resistor, the voltage, there's a voltage drop, okay, which is a reproduction of the half. Okay, which is what you see at the output. So the left-hand side is input, okay. Let me just quickly write, and here, of course, your right-hand side is output. Okay, what you get. Okay, so I said for the first half. Then, okay, can you let's follow me? The negative cycle now also comes in. But this time round, what happened? Negative and positive of a diode is actually reverse bias. Okay, I think last week I explained this diode. Forward bias, reverse bias to you. It's just the same thing. So very simple. If it's reverse bias, that means negative comes in, but I go to my anode, which is positive. So the diode now behave like an open switch, no current flow. Okay, simple as that. And then of course you see it's flat. Okay, here. All right. Okay, because no current flow. So there's no voltage drop across the resistor, no waveform here. Are you okay first? I pause for a short while. If there's anything you want me to clarify, please tell me. Thank you. Are you okay with the explanation for the half wave first? Any question? Any question? For the half wave rectifier? No? Okay, then I continue. Okay, so of course the next cycle comes in again is a positive. The same thing repeat, positive and positive of a diode, forward bias, current flows through, and then I have an output voltage again, the positive half. Okay, so if you look carefully, the diode is like controlling which half to pass. Only the positive half can pass through. The negative half is not because negative half will be reverse bias. So nothing, no current flow through, no voltage drop. So this is what you see on the right-hand side for a half-wave rectifier circuit. Are you okay? Can, so only, I repeat, only the positive cycle goes through because it's forward bias and current flows through the resistor, and then you have the voltage drop. Okay? Okay, so that explains the circuit operation in 2.1. If you have not followed me, you can read it on your own. All right. If you still don't understand, please ask me. Yeah. Or you want to ask me now, no issue. I can repeat the whole thing if you don't understand. Any question before I move on? Anybody? Any question? No? Okay, thank you, Chun Xian. Okay, so I move on. Thanks for your reply. Now I go on. Okay, so yeah, that is the operation of a half-wave rectifier circuit. Okay. So we move on a bit and try to look at the effective voltage. Remember when we say effective voltage, we talk about RMS value. So VRMS. Okay, be careful. Effective is RMS value. Peak voltage, remember that day we also talk about VM, voltage maximum, but peak voltage is, for example, over here, this is the peak voltage. Okay, and average voltage. Okay, now all these three terms comes about. We talked about that during the last session. Okay, VRMS, we revisit again how to calculate the same formula, nothing new to you. We have seen it before. If I want a VRMS value, I take 0.707 multiplied by VM. Just to confirm the VM is talking about peak voltage. That's why sometimes the notes I have to point out to you, or else you will be wondering how come for VM one. Okay, this VM is actually V peak. Okay, V peak, all right. Okay. All right. Okay, then if you still don't understand, I draw here quickly and show you example. Okay, example, this is my V peak. Okay, this is my V peak or VM. Okay, this is what it means. The tip of the waveform. Okay, the topmost part. Okay, and then you read off here whatever voltage. That is your V peak or VM. Same meaning both. I just point out to you. So if you don't see V peak here, you see VM, it's still V peak lah. Or you write V peak here, also nothing wrong because they are the same. Okay, but here I have find a bit strange because here they mention peak voltage and here they write VM. That's why I want to clarify for all of you. Same thing. Okay. All right, this is how you calculate your VRMS, and also, of course, you want to find the VDC, the DC voltage. Then you take 0.318 multiplied again by VM or V peak. Okay? That will give you the average DC voltage, which is over here. Okay? All right, if you convert to percent, it's 31.8% about that. Okay, there's a value here. Okay, this is your DC. Okay, then also they wrote here. All right, it's the same. They just point out to you. Okay, that's the thing. Okay, can so we move on. The next thing we talk about is a disadvantage of half-wave rectifier. Okay. Of course, obviously, just now you saw only one half of the AC cycle goes past. The other half is not allowed to go past. Yeah, only the positive half because of the diode. Correct. Then, because of that, then of course your average DC voltage is also very low. Okay, 0.138 VM or 31.8%, very low. Okay, just take note of the advantages, or sorry, the disadvantages or halfway. Okay. Then having said that, we move on to a full wave. Okay. Full wave, the word full wave means you expect to see both cycle of the AC going through. All right, and your output you should see both of the cycle being converted. All right, just now that one halfway, only one half. Okay, first thing first, Okay, so after just now we mentioned about the disadvantages, they tell you straight away that the full wave actually take care of the disadvantages that we mentioned just above here only. Yeah, okay. These are the disadvantages, but now I use full wave to take care of all these two, A and B. All right, and then they, of course, because of that, they produce twice the DC value of the rectified signal advantage, right? Okay, so this is the diagram that show you a center tap full wave rectifier. Okay, now for first part, they talk about the positive first. Be careful, one thing at a time. So now concentrate, can you all follow me? We are only talking about the positive half. Here I draw here. Only this one only. Okay? So what happens when this positive half comes in? It comes into here. Alright? Right? It will be forward biased with D1, the first diode, the top diode. Okay? And then here, right, forward bias. Because positive comes in. Alright? And then goes to the positive of the diode. And then positive diode, your forward bias. Of course, current will flow through, the arrow shows here. Okay? So when the current flows through, there's a voltage drop across R. Yeah? Okay? And then you see this at your output. Okay? I'm talking about positive half first. Don't jump first. First half only. Okay, can come in positive, forward bias, current flow past the resistor. The voltage across the resistor is shown here as the output. Yeah, we are talking about the top half only. Okay, top half first. Okay, this top half also like behave like just now the half wave like that. Yeah, I only allow the positive to go past. Okay, yeah. Of course, when this is D1 is positive, so-called over here, and is forward bias, D2 is reverse bias. That means no current flowing through D2 at the moment for the first positive half. Okay? And also D1 forward bias, D2 reverse bias. They don't both conduct together. Take note. Okay? So D2 is open circuit. Okay, then move on. Okay, now we talk about the negative cycle. Okay, just now was positive, now negative. I just highlight to you first. Meaning here, negative cycle. Okay, now negative cycle. All right. Okay. So when this is a negative cycle, what happened? This one becomes forward bias. Negative cycle comes here, then this one becomes forward bias. Yeah. Okay, so now D2 start to conduct. All right. And current indicated by the arrow start to flow. But you realize the current flow direction is same as a positive just now, also flowing through this way. Positive to negative. Okay? And of course, forward bias, and that's how you get your second half here. Okay? The next one. All right? But then some of you may ask, how come negative cycle go past here, then become positive here? Okay, listen. The reason I just said, when the negative cycle comes in, first thing first, D2 is forward bias. That means current will flow through like this arrow. So just now remember the positive sign and negative sign is here. It is the same direction as the first half. Okay, that is the reason why it is a positive half here shown at the output. Okay, can same direction, not opposite. So current probe pass through the resistor from positive to negative, you will get a waveform on your output, at your output. Okay, of course now when D2 is forward bias, of course D1 is reverse, not working or open circuit. So the opposite of the earlier diagram. Okay, so you take, so to speak, take turn to conduct. D1 conduct, D2 switch off. D2 conduct, D1 switch off. Okay, and that is how you get your full wave output here on your right hand side. Okay, so now you see, you can safely say that, oh, the entire AC circuit have been converted into DC. Right, for both half, not only positive half, the negative half also. So yeah, that's what you get output. Okay, can? Okay. So having said that, if now two diodes, or rather it become a full wave, then your voltage DC here will be double. That's why now you see your VC or voltage DC is 0.637 VN. Okay, the earlier one, the half wave is only 0.318, only one half. Because now I see both. All right, I see a complete full wave for both cycles. That's why my voltage DC equals to 0.637 Vm or Vp. In other words, it's 63.7% of the Vm or the Vp. Okay, can? Then of course they also mentioned the advantage, which is just mentioned, all right, okay, larger, which is this one. Okay, because for half wave it's only 0.318. Now I got 0.637. As good as double. Yeah, for the same peak output voltage. Okay. And then there's a disadvantage here also mentioned. But here they require a center tap or transformer. Okay, right? Now center tap, I think transformer, I think some of you may know, is quite a bulky component. Very hard to make it small. All right, this is a so-called a disadvantage. All right, can? Okay, I pause for a while and see if any of you want to ask me anything for this full wave center tap using transformer, the center tap transformer. Any question? Anything you want me to repeat or clarify? Anybody? Anyone wants to clarify anything regarding the full wave center tap? Okay, if no question, I take a 10-minute break because I think quite a fair bit for you. All right, after you come back from the break, 10 minutes, 10 minutes, then we move on to the next one. This one is very important because I think you will encounter this in your practical. All right, and you really need to handle this properly because later I'll tell you why. So now we take a 10-minute break first. When you come back, I will continue with this full wave bridge rectifier, one of the most common rectifier circuit for electronics. Yeah, so I want really some attention. Okay, so I'll give you a break first, and then we come back and continue. Okay? Any question? If not, I see you in 10 minutes time. Okay? Thank you.
you.